We've all seen the solar system pictures in textbooks, the Sun, slightly larger than Jupiter. But that isn't the right depiction of the scales. The Sun is so massive that you could fit about 1,000 Jupiters inside. Impressive as it is, our Sun isn't the biggest star in the universe or even our galaxy. That title goes to Uy Scuti, and compared to it, our star is like a tiny pebble. But there's more. Scientists have stumbled upon something even more mind-boggling, an enigmatic ancient star with a black hole inside. It's an astronomical mystery that both puzzles scientists and can potentially explain how the universe came to be what it is today. But how is it possible for a black hole to exist inside a star? Why were these stars so gigantic? And what would happen if a black hole star wandered into the solar system? Stars are like cosmic blacksmiths. In their fiery cores, they're forging the majority of the elements we observe in the universe. But the stars that could have existed at the very beginning of the universe were something different. Instead of conventional stellar cores, they harbored black holes within, allowing them to grow to unimaginable sizes and beyond. Ordinary stars arise from the clouds of gas and dust as gravity makes the densest regions of the cloud collapse. The resulting mass of material heats up and creates a protostar, an early stage in the evolution of a star. Eventually, the newly formed hot core accumulates enough matter from the surrounding rotating disk of gas, becoming a main sequence star that starts producing energy through nuclear fusion. It took our Sun about 50 million years to reach this phase. But these celestial giants weren't just large, they were so huge, their size allowed them to absorb the explosive force that would otherwise shoot the star's outer layers out into space. Instead, these ancient stars only experienced implosions, which transformed their stellar cores into tiny black holes while keeping the outer layers intact. If you could somehow observe this phenomenon from a close distance, you wouldn't even notice any changes with the star. Now that there's a baby black hole inside a quasi-star, it starts eating it from the inside. At this point, the black hole is tiny, but it's spinning, and this creates a disk of hot material circling it at nearly the speed of light. On top of that, there's no longer a limit on how fast it can devour gas as the star's pressure sends it straight into the black hole. The friction within the accretion disk becomes hotter and hotter, emitting tons of radiation and making the host star glow like a small galaxy. Quasi-stars, if they existed, grew faster than any black hole we've ever observed. Eventually, within millions of years, some of them would beat the largest stars and black holes in size that we know about, like Stephenson 2-18, Uy Scuti, and TON 618. Just how large is that? From thousands of times larger than the Sun to potentially even the diameter of our solar system and beyond. But this gargantuan size and mass also causes problems. The larger quasi-stars become, the shorter their lifespan. Our Sun has been around for over 4 billion years, with approximately 6 billion years left in its lifespan. As matter spirals toward a black hole, it goes faster and faster. Because of this, about 42% of this matter can be converted into energy. And this radiation is so powerful, it can push some of that incoming material away, just like a car tire pushes the air away. This process is so efficient, the radiation emitted away surpasses the energy output from nuclear fusion in stars. Just imagine a future where we find a way to harness this energy and use it for our needs. Even supermassive black holes with a large surface area that attracts matter have this limit. They are at the center of almost every galaxy out there, and some of these supermassive black holes have been recently discovered to be much larger than we thought. That's one of the greatest mysteries in astronomy. The gradual accumulation of matter over the age of the universe fails to explain their enormous size. But there's something that might unravel the mystery. Black hole stars or quasi-stars must have been the largest celestial bodies to ever exist, dwarfing even the most gigantic black holes we've discovered so far. Today, the conditions of the universe do not allow black hole stars to form, but at the beginning of time, space was packed with massive gas clouds. Within these dense regions of space, material collapsed in on itself under its own gravity, and because there was so much more of it, it piled up, giving rise to baby stars of extraordinary magnitude. Although there's an idea that they may have originated from dark matter halos, invisible spherical regions of dark matter of up to 100 million solar masses, where thousands of supermassive stars could form. Normally, large stars would go supernova and leave behind massive black holes. The majority of stars will spend most of their lifespan as main sequence stars. But eventually, they will all either become white dwarfs if their mass isn't big enough, or go supernovae. After a star blows up, it can end up as a black hole or a neutron star, and the path it takes depends on how massive it was. When our Sun runs out of hydrogen in about 5 billion years, it will turn into a red giant, expanding 200 times in size before finally shedding its outer layers and transforming into a white dwarf, a celestial object that's roughly 200,000 times denser than the Earth but about the same size. This dense sphere will then slowly cool to about 18 million degrees Fahrenheit, 10 million degrees Celsius, and in about 10 billion years, the white dwarf Sun will crystallize. The process is somewhat similar to how water turns into ice, although the material is different. In the case of the Sun, it will be carbon and oxygen solidifying. And stars over 10 times the mass of the Sun will have a different fate. They're big enough for their cores to collapse after a supernova, but they lack the mass required to become black holes. So where does this leave them? Deep inside these stars, the extreme pressure squeezes every proton and electron so tightly, they merge to form neutrons. Neutrons cannot be compressed any further, so they counter gravitational pressure, and the star finds a new balance. Neutron stars are the densest objects in the universe apart from black holes. They can be just the size of a small city, roughly 12 miles, 20 kilometers, but still have a mass of the Sun. On Earth, neutron star material the size of a sugar cube would weigh as much as 1 billion tons, about as heavy as a mountain. But how do stars become black holes? While the star is still active, the two prevailing forces work against each other: nuclear fusion and the intense gravity created by the star's own mass trying to squish it. Once there's no fuel left to power nuclear fusion, there's no longer a force to counter gravity, and the star collapses in on itself, just like the controlled demolition of a concrete building. Einstein believed that anything could become a black hole if it had sufficient mass and was compressed inside a certain radius. Black holes keep on growing throughout their lifespan, devouring any material that gets too close. When this happens, the region where gravitational pull becomes so strong that nothing can escape increases, and the black hole consumes even more nearby material. It's somewhat like the sinking of the ground due to the collapse of underground structures. Although with black holes, it is a gravitational sinkhole, gradually accelerating as its event horizon grows. Normally, black holes have a limit on how fast they can expand. This happens because of something called the Eddington luminosity limit. Basically, it's the point at which a black hole can't take in material faster than it already does. If you were filling a car tire with air and it had small holes in it, the increased pressure inside would make some of the excess air escape. In space, something similar happens with rotating black holes.